Welcome to springlib.
In this problem, we need to answer three different questions regarding the relationship between the standard cell potential and temperature. We are first given these two equations for the change in Gibbs free energy at standard conditions, and we need to combine them and rearrange them in order to derive an expression for the standard cell potential as a function of temperature. So since we know that our derived equation needs to be one for finding the standard cell potential, and that the standard cell potential only appears in this equation, it's reasonable to assume that we should begin by isolating that term from that first equation. So the standard cell potential, E, is equal to delta G at standard conditions divided by negative NF. And that's just from rearranging that first equation that we were given. And now we see that the second equation gives us an expression for delta G at standard conditions that we can substitute into the numerator of that rearranged expression from the first equation. So when we substitute that in, the numerator now becomes delta H at standard conditions minus T delta S at standard conditions divided by negative NF. And the next part of this question asks us how we can determine the values of delta H and delta S at standard conditions if we have values, experimental values that we can measure for the temperature and the cell potential. And in order to determine these values graphically, we need to rearrange our derived expression for the standard cell potential as a function of temperature to form the equation of a line so that we can easily see how, when we graph out those two values, that is the temperature and the cell potential, knowing that temperature is the x variable and cell potential is the dependent y variable. And so we know the equation of a line, y equals mx plus b, and so we can rearrange our derived expression in order to find that form of that graphical line equation. So the standard cell potential is equal to delta S at standard conditions divided by NF times the temperature minus delta H at standard conditions over NF. And again, this was just done by further simplifying our expression for cell potential as a function of temperature. We did negative T delta S divided by negative NF to give us positive S over NF, and we left temperature out there since we know that that is our independent variable in the equation of a line and therefore corresponds to x in the general form of a line, y equals mx plus b. And then we also did delta H divided by negative NF, which is minus delta H over NF. So now we can see that we have the form of a line, y, the dependent variable of cell potential at standard conditions, is equal to m times x, which is a temperature independent variable, plus b. And so, again, this is the expression, the answer to the first part of this question for the cell potential as a function of temperature. And for the next part of the question, how we can determine what delta S and delta H are given data for T, which is the independent x variable, and cell potential, which is the dependent y variable. We can see that from the equation of the line that if we were to plot the cell potential as a function of temperature, so if we plot cell potential versus temperature, then the slope is equal to m, so delta S at standard conditions over NF, and the y-intercept of that graph of the line is equal to b, so negative delta H at standard conditions over NF and F is just Faraday's constant, so we know that, and N is the moles of electrons, which we can determine from the cell reaction taking place. Then if we were to plot cell potential versus temperature, find the slope and y-intercept, we could multiply each one of them by NF, which we can find to isolate delta S and delta H at standard conditions. And so that is how we can graphically determine both of those variables based on the relationship between cell potential and temperature. And now the final question that we are asked is, how can we, what property should we change so that the cell potential is relatively stable regardless of temperature? And so if we look at our equation again, we can see that we multiply that temperature by the slope. And Faraday's constant and N, those are constants that we cannot change. And so the only thing that we can look for is a reaction, a cell reaction with a very small value for the change in entropy at standard conditions. Because if that were to be 0, then if we multiply 0 by that temperature, then the slope would be 0. And that means that if we change the temperature in any way, we multiply it by that factor of 0, and so it would have no influence on the slope of that line. And so that is why at low values of delta S at standard conditions, then that relationship between cell potential and temperature indicates that the temperature dependence diminishes. It decreases to the point where if delta S were to be 0, then it wouldn't matter how we change the temperature at all, because it would not be, the cell potential